My name is Aman Tiwari. I'm a solutions architect at AWS. In today's session, we are going to talk about Ripple and how have they built an AI-powered operations platform to transform their platform operations using AWS. I will now hand it over to Vijay, who's going to get us started.
That being said, us being in the Ripple platform team, monitoring the resiliency of the network is one of the challenging problem, right? For example, in a centralized ecosystem, it's very easy for us to figure out what is going on when we launch a new feature, where like you can just go to a database and you can execute a query before the change, after the change, you can easily figure out what's going on in the network. But when you talk about a decentralized ecosystem, particularly 1,000 nodes run by many independent operators like universities, blockchain institutions, wallet providers, financial institutions, it's very hard to identify how the network is behaving. As we in the RippleX platform team, we are in the trenches all the time in terms of making sure XRPL is more secure, resilient, and robust. Particularly in terms of solving these problems, one of the things we always end up having is like we rely too much on C++ experts. For example, like the whole protocol is written in 2012. It's a huge code base. It's all C++. So when an issue happens or when we want to monitor the network, what we generally do is like we get this whole huge volume of logs, and we try to make sense of these logs by looking at the C++ code, and it's so complex, we have to rely on the C++ experts for us to make the understanding of what the pattern of the issues, right? So for example, I'll give you, 4 weeks ago, there was a Red Sea cable cut happen. And some of the node operators in the Asia Pacific, they were having reliability issues, right? So when we got all those issues raised to us, we end up asking them, okay, can you give us the logs? Then we get all these logs, which are huge volumes in size, which is almost 30 to 35 gigs for a single node. And then we go to our machines. We take all those huge volumes of logs. We end up doing a cross comparison. And all these logs are debug logs. And if you know it's a peer-to-peer network, you get a lot of signals, cryptographic details, proposals, peer connections, and to make a meaningful summary of what's going on is one of the most complicated process, particularly when you're solving a production problems, right? So it could take almost 2 days even to just understand what's going on. And even those cases, like we have to rely on a C++ expert, like Core Ledger team, who's an engineering team who does all this protocol development, for them to get involved and to make us a meaningful summary out of it. And logs are the goldmine of the information, and it plays a very critical role. And we've been doing this forever. One of the things that we wanted to change was like how AI can solve this problem for us, right? Why do we have to rely on C++ experts? Where the whole world is heading towards English as a natural programming language, we started looking into AI as a solution where we can correlate between the logs and the code, and it can give us a meaningful summary out of it. That's when the whole journey of log and code correlation of solution that we started looking at. So that being said, this is probably the most lightweight, high-level design. You guys going to look into it. My partners who are wearing the suits, they're going to come with the big guns of whole deep dive architecture. So if you are engineers, you're going to be in for a treat. There is a lot of good stuff that's going to be talked about. But on a very high level, I want to call out these 3 boxes, right? So the middle box, the multi-agent platform. So this is the brain of this orchestration. So where this is a foundational layer that we built leveraging AWS stacks. This contains 2 agents at this point, and we're also working on 3 more agents, which Hari would be giving us more detailed walkthrough. So this is primarily the orchestration layer where the agents work when a user sends a request via a chat interface. They make a code path of whether it can go towards a code analysis pipeline or a log analysis pipeline. So the second half, this is where the bulk of the data preparation happens. Since the code is an open source repository, so the log code analysis pipeline, what we do is like we have a everyday periodic code retrieval that is run from the GitHub repository. So every commit which goes into the develop branch, which gets prepared, which gets stored in a graph DB for us to make a meaningful summary out of it. Then we have log processing pipeline. Since we are talking about huge volume of log, which is almost 35 to 50 gigs for a single node, and Ripple almost operates like 40 plus machine in mainnet, that constitutes around 202 to 2.5 petabytes of data. So to have all these data ready and prepared, we have this log processing pipeline which runs every day, which makes it prepared for the whole agentic framework to make a meaningful summary out of it. So that being said, I'm going to call on Hari next to come and walk you all through a detailed architecture. Yeah, over to you, Hari.
Switch me on. Cool. Hey all, this is Hari Vignesh Rajendran. In the forthcoming slides, we will talk about the log processing pipeline, the code processing pipeline, and the graph RAG capabilities that we have built. First, let's talk about the log processing pipeline, which brings the nodes logs to CloudWatch. Raw logs from validators, hubs, client handlers, they are first brought into S3 using a separate workflow, which we have orchestrated through GitHub workflows using SSM. Once the data reaches the S3, we have the S3 event trigger triggering the Lambda function there, which looks into the file, gets the byte start and end of each chunk, and which also respects the log line boundaries and also the configured chunk size. And once these messages are derived, they are then put into SQS for further distributed processing. So these messages are then read by the log processor Lambda function. It actually retrieves only the relevant chunks from S3 based on the configured chunk metadata that it read. And it parses the log lines, gets the metadata out of it, and puts these log lines and metadata to CloudWatch. Now let's move on to the code analysis pipeline. So here we have two main repos, the RippleD repository and the standards repository. The RippleD repository holds a server software for XRPL ecosystem. And the second is the standards repository, which describes the standards and specifications relating to XRPL ecosystem to ensure interoperability between the XRPL and other applications that are built on top of it. Both repositories feed into our pipeline using Amazon EventBridge, which is a serverless event bus. Using EventBridge scheduler within it, we automatically trigger repository syncs on a cadence. So once a sync event arrives, the Git repository processor pulls the latest changes from GitHub, including the code and the documentation, versions them, and then stores into S3. Then comes the knowledge base ingestion job, the sync job, let's say, which pulls this data and puts it into Amazon Neptune Analytics vector store. We will look into this in more detail. So knowledge base, by default in the backend, it configures the chunkings, embeddings, and acts as a vector storage as well. OK, so now let's move on to the next slide. So we want to actually dive a little bit deep about the graph RAG capabilities that we have built. So we are not using the OpenSearch vector store here. We are using graph RAG. That's because it's really good at storing relationships across the code base. So I will detail that here. So we have the file stored in S3 now. The process starts by reading these files. The knowledge base sync jobs reads these files in, converts these files into smaller manageable chunks. Bedrock also, as you would know, that it allows multiple chunking strategies, fixed size chunking, and other LLM-based approaches. In our use case, we use fixed size chunking because it works well with structured content like code and documentation. So once these chunks are derived, they are sent into the Titan text embeddings v2 model, which generates the embeddings, which is the actual semantic meaning of the text. Yeah, so also you would notice that there is a box underneath the Titan text as well. So this is the extract entity step that happens. So what it does is it looks into the chunks, derives related entities being function names, code calls, and the classes, modules, and other domain-specific identifiers. The Claude IQ v1 model gets all this information, and this information is then used to build a lexical graph. So this lexical graph uncovers all the relationships across our code base. So this is what makes the retrieval very fast and very efficient for us, utilizing a very lesser context window for the LLM. Okay, so once these chunks, embeddings, and entities are retrieved, they are then sent to the Neptune Analytics Graph Store. This is where the graph is built. The lexical graph I talked about is nothing but nodes and edges, which has links to the entities, source chunks which belong to which source document, and the cross-document relationships are all stored here. This Neptune graph database becomes a powerful retrieval layer after all these magic that happens in the backend for us, which is managed by Bedrock. So what happens when the query comes in? So the code analysis agent using an LLM which is hosted in Bedrock first gets this context from the knowledge base along with the entities. Then it is sent to the LLM for generating responses, which is not only grounded in semantics, but also on the code relationships as well. Okay, we also have applied another, let's say, significant improvement as well. So we have re-ranking layer built on top of this graph RAG workflow. So re-ranking is a powerful enhancement to RAG. It adds a second and a more intelligent pass over the retrieved documents, while the vector search gives us the top matches based on the embeddings. Re-rankers like Cohere re-rank that you see here evaluate the relevance dynamically at runtime. This means that the model reads both the query and each candidate document together, allowing it to understand nuance and give out better results for the LLM. So here's how Ripple applies it. We first retrieve like a broadest chunk of data from knowledge base. We then give that to the re-rank model along with the user query. The re-ranker model then calculates a relevance score from 0 to 1, 1 being the highest score, and then it reorders the results, and let's say it returns the top 10 results back to the LLM. So now you get like fewer results to the LLM, but they are all very high quality, so that the context window is not affected for the LLM, so you still have more tokens to burn, essentially. So you can see this question here, why we have had the screenshot. I've asked the question about what log messages are defined inside a function. This actually forms the premises of the entire presentation here. So we need to find the right log messages to query in our log files. So you can see the source chunk that it shows is number 1, but originally, without the re-rank model, it was actually number 4. Because of the user query that we gave it, and also the chunks that were retrieved, it was able to combine them together and give us the top results.